Hello everyone. Welcome to the next lesson on further GCSE math. So we're continuing with calculus, or I should say, today we're really getting into what calculus is. So last time we was looking at just limits, which is a necessary prerequisite that we need to understand in order to understand calculus, more specifically differentiation, which is about the study of change. And we're going to be using those techniques of limits in order to understand what differentiation is. So we're going to look at finding um, the derivative of an equation, essentially differentiating an equation from first principles, and what this derivative actually means, like as a gradient function, essentially the rate of change of that function. Um, then we're going to look at how do we actually differentiate functions in practice, because we don't always want to work things out on first principles, like as in like literally from the definition of what differentiation is. We want to look for patterns that can help speed things up and do it more quickly. Um, and then finally, we're going to look at turning points. So, as part of the regular GCSE math syllabus, you've perhaps seen the turning points before and of a quadratic equation. Um, by completing the square on that quadratic. Now we're going to look at finding the turning points of a general equation. So not just quadratics, using differentiation, which is easier as well. And completing the square only works with quadratics anyway. So we want something that will work in general. So that's the plan. So let's look at first principles. So how do what actually is differentiation, and then how can we differentiate a function based on that definition? So differentiation is the process of finding the gradient of a function. So you guys should already be quite familiar with finding the gradient, say, of a linear function, and you just get some number. And the reason why you get a number is because the gradient of a linear function is constant. It's like a straight line, and it's always just going up at the same rate, or perhaps going down at the same rate. Um, However, so we've seen with linear equation, it's always going to be constant. However, the gradient of a non-linear function, like say a quadratic or a cubic equation or something else, um, its gradient will be another function because the gradient is constantly changing because it's a curve. It might be going up and then it's going down and it might be going up again and so on and so forth. So it's going to be another function, and we want to find out what that function is. So then, given any point, any x value, we can then find out what is the gradient at that point. So to find that gradient function, we need to employ the use of limits, like what we learned about last time. So say if I have a set of axes like this, and I'm going to draw a rough function, f of x, you might identify that this is going to be a cubic function, but we're just looking at a general f of x at the minute. And say we want to find the gradient at this specific point. So we want to find out what is the slope at that point. Essentially going to be the slope of the tangent line at that point. How do we do that? So what we do is say we take another point further along like this yellow point that I put in. And say if we draw a straight line through those two, and we want to find out the gradient of that straight line. No problem. Like we've done this, plenty before, where you've got these two coordinates. What we'll do is we'll do the difference in y divided by the difference in x, and that will get us the gradient of this straight line. But you can quite clearly see that the gradient of that straight line is not going to be the gradient at that specific red point, which is what we want. Okay, well, what about if I move that yellow point closer to the red point? Like maybe very close like this. And you can see the gradient of that straight line is now going to be very close to the gradient specifically at that point, that red point, but not quite. And if we, zoom in on that point to take a closer look, it's very, very close, but not quite. But let's say, okay, we're just going to approximate the gradient at that red point instead. So let's do our difference in x, difference in y, which we, often label like this, delta y, delta x. It means like small difference in x, small difference in y. And by doing that division of delta y over delta x, we can get the gradient of that straight line in the same way you guys should already be familiar with. So let's put that as an equation. It's going to look something like this. So delta y over delta x. So delta x by definition is your your difference in x. Now we want to know what is the difference in y based on that difference in x. Well, it's going to be that numerator there of that fraction, because okay, we're looking at a point x. The corresponding y value at that point x is going to be f of x, isn't it? By putting it into the function, we get f of x, which is the corresponding y point, and we want to look at the difference between that point and some point slightly ahead of it, not at point x, but at point x plus delta x, so some slight point ahead. And so the y value at that point is going to be f of x plus delta x, in brackets there. And so you can see by finding the difference between those two, that will give us our difference in y. So that first term, f of x plus delta x, is like your y2 value, and then f of x is your y1 value, if you want to think of it in terms of like y2 minus y1 over x2 minus x1. The difference between the x's will, by definition, be delta x. So that equation, I hope, makes sense to you based on what you already know about finding gradients of a straight line. If we now want the gradient specifically at that red point of the curved line, what we do is we find the limit as that difference between those 2 points essentially goes to 0. And essentially that yellow point is going to go on top of the red point. It will become the same point. And that's where you get then this notation dy dx over dx, which is what we then refer to as the derivative or the gradient function. And this is going to be essentially a function of x, and the values of this function of x will basically tell us the gradient of f of x at various values of x. So I appreciate that's quite a complicated function there. And yeah, so you see the delta y and delta x have turned into this dy dx. Dy and dx are like infinitely small changes in y and x. As we find this limit, as the change in x and the change in y essentially go to 0. That's the notation we use there. So, bit of a new concept there that I hope you guys can wrap your head around, and it's basically taking this idea of finding a gradient that we're already familiar with, and by using limits, we can find the gradient at a specific point on a curve. And yeah, when we take that limit, it's essentially doing this, where the yellow point moves on top of the red, and now we've got specifically the gradient at that point, essentially like the gradient of the tangent line at that point. So how on earth would we do that? How would we calculate that? So to differentiate from first principles, we basically have to substitute our function we're trying to differentiate into this formula and apply the techniques we've learned to calculate limits. So this formula that we've got here, and it's differentiating from first principles can get quite complicated for certain functions, but you'll only ever get asked something that is like a relatively simple function. So say this one here. So if we just simply have y equals x squared, so you can see that's essentially a quadratic. It's a non-linear function, so we're not going to get a constant gradient. Say if we now want to find this gradient function for it, so dy dx, this is essentially our gradient function. It's going to be this. We're finding the limit as delta x goes to 0 of our f of x plus delta x minus f of x all over our change in x. So you see, if I put x plus delta x into our function here, 3x squared, you see you get this, 3 times x plus delta x squared, and then just at x, it's just 3x squared, isn't it? And we'll find the difference between those two. So you can see there, that is going to be essentially our difference in y, isn't it? For a general point x and another point slightly ahead of it, x plus delta x. So yeah, I hope that makes sense why that would be. Now it just becomes a matter of solving this limit. So if you put in delta x equals 0 into this, you notice you're going to get essentially 0 over 0. And we learned in the previous lesson, when you get something like that, you can essentially, that's like a removable discontinuity. Like we can essentially remove that, because 0 over 0 is essentially going to just like blow up to infinity essentially. But that's like a something we can essentially remove. How are we going to remove it? Well, the key to doing that is we essentially want to cancel out that factor with the denominator. So we want to essentially cancel out that delta x. So let's see if we can do that. Let's play around with the numerator there. Let's expand it out, say, and collect like terms. See what happens. So you see that x plus delta x squared. If I expand that out, and you see the whole thing is getting multiplied by 3, you see you're going to get these terms here. And notice that 3x squared is going to cancel out here. We've got 3x squared minus 3x squared on the other end of the numerator. So if we cancel that out, you're essentially going to get this. Okay, what can we do with this? So you might notice here that there's a common factor now of delta x. Everything here is being, every term on the numerator and denominator has got a factor of delta x. So what we do, let's divide everything by delta x. So now it's essentially, the denominator is going to essentially disappear because you're now over 1. And you get 6x plus delta x. Now we've essentially removed that discontinuity. We've now got something where we can just substitute in delta x equals 0. And you see we get 6x. So there we go. That's now our gradient function. So for any value of x, say x equals 2, what I can do is I can substitute that into this. So 6 times 2 gets me 12. That tells me that the gradient of y equals 3x squared at x equals 2 will be 12. Or I could substitute in the value of x equals minus 1, and you see we're going to get dy dx equals minus 6. That tells me the gradient of y equals 3x squared is minus 6 when x equals 1. So you see at different values of x, we get different gradients. So that's one example of finding a derivative from first principles. That's typically, all you'd be asked, something like a little monomial like that, where you've got a number times x to some power. But you also might get asked something like this. Say if you had 1 over x, which, remember, we could rearrange this to essentially just be x to some power, like this would be x to the minus 1, wouldn't it? You could put it like that. I'll prefer to keep it as a fraction for now. Let's say if I'm trying to find the derivative, this gradient function for this y equals 1 over x. So dy dx, again, we apply the formula. So we're notice I've used a slightly different notation here. So rather than having delta x everywhere, sometimes we use the letter h instead, just to make it a little bit neater. So yeah, make sure you're comfortable with that, because that is a notation that's quite commonly used. So you see here, we've got basically, say if f of x equals 1 over x, we've basically got f of x plus h minus f of x on the numerator. And then on the denominator, we've got our difference in x, which is just h. So a bit complicated, a bit more complicated this one, because we've got fractions inside fractions. How are we going to do this? Again, you find this is always going to be the case. If you just substitute in h equals 0, you're essentially going to get the limit of 0 over 0. And so, yeah, again, it's a sign of a removable discontinuity. That is something we can solve, but we need to cancel out that h essentially on the denominator again. So what can we do? Well, first of all, I don't like fractions inside fractions. It's a bit messy. So I'm going to rearrange it like this, where I take that division by h, I'll put it as a times in by 1 over h. And on the inside, you see, is of the brackets is just the numerator now. Just makes it a little bit neater. This is, something you can do as well if you want to. I think this just makes it easier. Okay, we need to get a factor of h somewhere so we can cancel it out. We already know that will happen. We just need to see how can we make that happen. So, okay, what can we do with those fractions on the inside the brackets there? Well, what we could do is perhaps bring it together into one fraction. That's normally a good idea. Like, rather than having multiple fractions, let's bring it together. So use your algebraic fraction techniques here. Get the denominators the same so you can bring them together, and you should get this here. Now what we could perhaps do is let's simplify that numerator, because you see we've got x minus x plus h. Well, you see, you're going to get an x minus x there, so that will cancel out, and you're essentially just going to get minus h on the numerator. Now you might be able to spot what's going to happen here. So you see there's a factor of h there on the numerator, and we're dividing by a h on the outside, aren't we? So that's essentially a factor of h on the denominator. You should be able to see that this is going to happen, isn't it? That h over h is going to cancel out. And we're just left with 1 over x times by x plus h. Now we're at a position where we can just substitute in the h equals 0. And if we do that, you see we're going to get minus 1 over x squared. And there we go. That's the derivative we've found. So the derivative of y equals 1 over x is going to be dy dx equals minus 1 over x squared. And again, substituting any value of x we want, and it'll tell us what the gradient, substituting any value of x into that minus 1 over x squared, and it'll tell us what the gradient is for y equals 1 over x at that point. So there we go. That's pretty much the only two kind of scenarios that you'll get asked to differentiate from first principles. Appreciate that is quite complicated. But once you get comfortable with it, that's all you really get asked. Because like I said, it can get very complicated once you go into more complicated functions essentially. So let's look at actually doing differentiation now, not from first principles. You know, we want to look for the patterns that will allow us to differentiate more easily and more quickly. So yeah, we don't want to calculate from first principles all the time. That takes too long. We want to look at rules that will help us go faster. And one such rule that you're going to use very frequently is what's known as the power rule, which we could write like this. So you see here, I've put this d over dx. So this is like we're treating differentiation like an operation now, where what we want to do is we want to differentiate this expression a times x to the power n. So we want to find what is the gradient function of this. That's basically what that means there. And in general, we'll find it's going to be this an times x to the n minus 1. So what actually is going on there? Notice all that's happening there is we're essentially multiplying by the power, and then we're knocking one off the power. So whenever we have something of that form, like a monomial, just a number times a variable to some power, it's always going to follow this pattern where you end up multiplying by the power and then knocking one off the power. So let's apply that to the example we just saw here. We do the derivative of 3x squared. Well, what we're going to do is we're going to multiply that by that power. So you get 3 times 2, and then we get x to the power of 1 less than that power of 2. So it becomes x to the power 1. And you see, if you work that out, it's going to essentially be 6x. 3 times 2 is 6. X to the power 1 is just x, isn't it? And that was the answer we got earlier. But you see how much faster that is, because this is a pattern that is always going to occur regardless of what the coefficient and what the power of that monomial is. And similarly for this one here, where we have 1 over x, well, we can write this as a power, can't we, like this? So we do the derivative of x to the power minus 1, and let's do the exact same rule. So what we do is we're going to multiply by the power. So we multiply by minus 1, and then we knock 1 off the power, so the minus 1 becomes a minus 2. And again, let's use our indices laws to go back to a fraction form. And you see here, look, we get the exact same answer again. And so yeah, for some of these like simple algebraic fractions, you can also, apply this power rule to differentiate them. More complicated algebraic fractions go a bit beyond the scope of GCSE, so you won't get anything like that. It will only be something simple like this, like 1 over x or 1 over 3x or whatever. So a couple other rules we want to be familiar with is what are called the linearity rules. So this is a few different rules we want to be aware of. Like say something like this, like say if a is some constant number, like 5, 10, 7, any number, if we do a derivative of that with respect to x, it's always going to be 0. Why? Because what we're basically asking there is how does this number change as x changes? Well, the answer is it doesn't. It's a constant. It's a number. It doesn't change. By definition, a constant doesn't change. So therefore, that the derivative is 0. which means, yeah, it's not changing at all. What about something like this? If rather than differentiating f of x, we're differentiating a times f of x, where a is some number. Well, here is an example of where what we can do is we can take that number to the outside, and we could just differentiate the function f of x and then times it by a, and it essentially will be the same thing. So that's another important rule. The most important rule we probably want to use here is this one, where say if we're doing the derivative of not just a function, but say a function that is the sum of two other functions. So say f of x plus g of x, and then we want to differentiate that. That's the same thing as differentiating f first and then differentiating g and adding them together. So that's a really handy rule to know as well, that we can just differentiate each part individually. Or like say if you had a more like say a full quadratic with an x squared, an x and a constant term, we can differentiate each term individually and then bring it together, which is really handy. So let's try applying that to this final section where we're not just going to differentiate a function, but we want to use that derivative, not just to calculate gradients at random points, but how can we find certain key points that we're interested in, such as the turning points. So we've learned how to find a gradient of a function, which is basically its rate of change. It tells us the rate of change at different points. Differentiation could be useful to find all kinds of points, so such as minima and maxima, which are basically turning points. We'll see those in a sec. Something known as inflection points, which I'll just touch upon today, but we're going to look at that in more detail next lesson. And also to find tangent and normal lines. Like we've already seen that the gradient at a specific point is essentially the gradient of the tangent line, but we can also use that to find the normal line or perpendicular line. Same thing, normal, perpendicular, different words for the same thing. So say if we take this graph of this function that we saw before, and we want to find the turning points. So the turning points are these 2 points here, basically where the function turns. So it was going up, but then it turns around and goes down. And then it's going down, and it turns around and goes back up again. Turning points. And these points are what we sometimes will call maxima and minima, because you see there, that first turning point is like a peak. It's like a maximum point. And then the other one is a trough, where it's a minimum point. But they're clearly not the maximum minimum points of the function as a whole, is it? It's because you can see to the right the function goes up to infinity, and to the left it goes down to infinity. So more specifically, these are what we refer to as local maxima and local minima. It's like the maximum point in the local area. It's like if you imagine yourself standing on top of a tall hill, and you might be at the maximum point in the local area, but you're not necessarily at the highest point on the entire Earth, are you? You can think of it like that. So, maximum in your local area or minimum in your local area. So let's try and understand this in terms of gradients. So you see there, I've drawn a little green arrow, and down in the bottom left there, it's pointing like up. We've got a positive gradient at the moment. And as we go up, the gradient starts to gradually go down until we get to that point here. And you see now the gradient is perfectly horizontal. And then as we continue, the gradient gets steeper, going down and down and down until you get to this point here, where it reaches its steepest point before it's going to start turning back. This is what we call a point of inflection. It's that turning point essentially of the gradient, where the gradient has kind of gone down, 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 and it's reached its maximum steepness before going up, up, up. And maybe it might inflect again, like maybe it keeps going up and up and up until a certain point, and before it then starts turning down again, and that will be another inflection point. We'll look at that in more detail in the next lesson, but that's another point. And you see from this point here, as we go on, the gradient just keeps going up and up and up forever. So, yeah, that's our turning points, our inflection points. Finally, tangent lines, normal lines. Again, we'll be looking at this more next time. We've seen that the gradient at a particular point is basically the gradient of the tangent at that point, and then we can use what we know about perpendicular lines to then determine the normal line, which is like perpendicular at that point. But yeah, today we're just focusing on the turning point. So let's get rid of that inflection point and the normal line. We're just focusing on these turning points. So the turning point, as you might have seen there with the green arrow, the turning points are essentially where that green arrow is horizontal, which is basically when the gradient is zero. It's not going up, it's not going down. At that point, that specific point is horizontal. It's not actually going up or down. And we can use that with our gradient function to find out what those points are. So, okay, so say if this function is this, it's this cubic equation. So you might already identify from our previous lesson on cubic equations, it has that shape, doesn't it, of a cubic. We can now differentiate this by using our rules that we learned earlier. So remember, we can differentiate each term individually, and each term individually, we can essentially apply the power rule to. So we find the derivative dy dx. So it's say y equals f of x here. Dy dx is then going to be this. So you see that first term, we times by 3 and then knock 1 off the power. The second term, we're going to get minus 4 times the 2 and then knock 1 off the power. And then when it comes to those last two terms, you don't even really have to apply the power rule at all, because that's essentially the linear part now. X plus 4. Well, we've seen from finding gradients in the past. The gradient there is just going to be 1, isn't it? It's just the coefficient of that x term, and the 4 is going to disappear entirely because it's constant. So you can still technically apply the power rule to those terms, but I find it's a lot easier if you just identify that that's essentially the linear part now. It's x plus 4, and so you know the gradient of that last two terms is essentially just going to be the coefficient of the x term, which in this case is 1. And there we go. We've now managed to differentiate that whole function just like that. We don't have to go from first principles or anything like that. So we want to use this now to find those turning points. So this is where we're going to use that fact that you notice that those turning points were specifically when the gradient is 0. So here's our gradient function. Let's find when does that function equal 0. And that will tell us where the turning points are. So you see here it basically ends up being a quadratic equation. You can just solve that equation any way you see fit. And you see we've got our various different methods. Use whichever one suits you best. I've used the quadratic formula here because you see the values actually aren't quite nice here. You end up getting decimal values. Then what we can do, so this basically tells us the x values at which the turning points are going to occur. So if we now want to find the corresponding y values, we need to substitute back into our f of x, which is what tells us our y values, not back into the dy dx function. That's basically just going to get us the gradient at those 2 points, which we already know is 0. What we want are the corresponding y points, so we need to substitute back into f of x, and we'll get the corresponding y values. And so we can put those on now. We know the coordinates of those turning points, which are super, super useful. It's something that's used all the times, like when you want to minimize something or maximize something. Like, a simple example would be like, say if you had some kind of curve and it's representing your like profits of a company or something, and you want to find where is that sweet spot, that maximum point where you're going to make the most profit. You want to be able to find that, and if you've got some equation that models that, that's one example of where this would be useful. But there are so many examples of where this is used. It's such a kind of general, powerful technique. So there we go. So we just looked at what differentiation is and turning points. Next time we're going to build upon that. Here's your challenge question for today to really test how well you understand this. So say if you have a cubic function and we have the turning points 1, 5 and 3, 1. Can you find out what the original function would be? So it's kind of like going in reverse here. Rather than having a cubic equation and trying to find the turning points, I'm giving you the turning points and I want you to find the original function. Now, this isn't enough information on its own. What I'm going to do is I'll give you the function here where you know what the x cubed term is, you know what the constant term is, but the x squared term and the x term, they've got unknown coefficients b and c here. And can you use your understanding of differentiation along with the fact that you know what those turning points are to then find out what b and c are going to be? And if you need some tips, so if you want to just go and give this a go yourself, go for that now. If you want some tips on how you might do this, here are some kind of key steps and how you would do this. So we want to find the derivative of f. Sometimes we use it, we denote this as f dash of x. We'll see that more in the next lesson. Basically, you find the derivative of this. That derivative is necessarily going to be in terms of b and c, isn't it? And what we can do is we can make use of the factor theorem and the fact that we know that those turning points occur when this derivative is equal to 0, to get a couple of different equations, which is kind of what we need, isn't it? Because we've got two unknowns here. We need two equations, and then maybe comparing coefficients, simultaneous equations, we could find out what the B and C is. So I've kind of given you some tips there on how you could go about solving this. But yeah, give that a go. If you can work that out, then yeah, very well done, because that's a challenging problem there. But yeah, that's it for today. So we've introduced what differentiation is, this whole idea of rate of change of a general non-linear function. And next time, yeah, we're going to be building on this. We're going to be looking at something known as second order derivatives. And we're going to use this as well as what we've seen today to find other key points, like we saw the inflection points, or we could find like the like parallel, like a tangent line or a normal line, for example. So yeah, I'll see you in the next lesson for that.